Here today, I have to talk about building reliable applications. So we all want to, for our applications, our systems, to be reliable. What does it mean? And the usual answer in software engineering is it depends. And it really depends on the business requirements, business risk. It's to what measures we want to take to counter the business risk, the probability of the risk, and what kind of cost we want to pay for the solution. And it's not just a cost of building, it's also cost of operating the solution. It's also an opportunity cost of not doing something else. Let's start with the simple case. Let's say I'm running a relatively non-critical, simple application, stateless. I don't have anything there to start. Like if you attended the keynote today, I'm sure you all did, like an example that Sebastian was building, kind of API app, or fast API, that runs stateless. It has some code, some configuration, but you can see if we kill like a pod, one instance of application, we can start another one. There's no problem. It's very easy. And so like the analogy I see is this old fable of the three little pigs. Like the first pig built a house that really had out of straw. And these kind of applications are analogous to that. So if angry, hungry wolf comes and blows that straw hat, the pig can run away and build another one quickly because what it takes to build one. And then it can run away again. So that's kind of the case with these simple apps that we can just restart the pod. Now, most applications have some state, and state is just a fancy kind of academia word for data. You have some data to store. And if the stateless application I can run anywhere, I can run in my basement, I could just attach a server because who cares? I could run it anywhere. When I have data, like a database, for example, now my kind of risk calculus is different. I don't want that data to disappear. I cannot afford anymore to run it in my basement because the hard drive may die, the machine may die, I may lose data. And usually the solution is to use some kind of like, today it's the easiest way to go to the cloud. Back in the days, there are other solutions, but today you just have like network attached storage like that is backed up like EBS in AWS or managed drives in Azure, and that guarantees durability of our data. That means even if my server crashes, even if everything dies, data is preserved. I will not lose my data, the most precious part. And just to note that I'm using database as kind of simplify examples. Usually systems are more complex. They have other stateful things. They have like queues. They have multiple databases. They have other things. But the concepts are the same. So let's talk about it as if it's a single database. So let's pretend that's all we have. So we solved the durability by using some kind of like replicated, persistent, and network attached disk. But what about reliability? Like even if our database has data preserved, if database process crash, and we restart it, like on a different VM, a different pod, it may take minutes for it to come up. Sometimes it's even longer. And we go back to this trade-off question. What is the business risk? Can we afford for it to be down for several minutes? And the answer is yes. We don't have to really complicate things. We can live with that. We can occasionally, and it doesn't happen that often, except for we need to upgrade database. We need to apply patches. So like that's why sometimes still in 2025, I see on some like the US banks websites, usually Saturday morning, say a system is unavailable due to maintenance, which is kind of like a weird concept, but some companies still do that. And so if we can afford to be in that world, that's fine. Durability is enough. With this kind of scheduled downtime or some infrequent downtimes. But what if that's not enough? So if with that system we just have durability, we build sort of like a stick house with the second pig that hit there. It's better than the straw house, but it's still not as solid as it needs to be for something that needs to be available. Like if we need the application to be available 24/7, and these days people are used to that. They're used to their services on the phone, on the websites to be always available. Whether they're critical or not, the people get upset when things is not there. So usually we want availability today much more than even like 10 years ago. And back in the 90s, when you needed something highly available, you would go with very expensive, very complex systems like, for example, this tandem non-stop system, where you could hot swap CPUs, you could like replace hardware. was very expensive but very important for things like financials for banks. These days, we do it differently. We can get like a replicated database from a cloud provider, like, for example, RDS, Aurora, or the Cosmos DB, or Spanner. And inside the service, they do all the complex stuff. They run multiple instances. They replicate data. They have multiple compute instances. So if they need to apply an update, or upgrade the server, or apply a patch, they do it one instance at a time for us, so that they make it invisible that some downtime is happening, because there is no downtime for the whole system. And we could do it ourselves. We could self-host some open source database like that, but usually it's not worth it. It's not worth the effort. Again, the cost of operating them, the cost of people that would deal with that. And we happily pay for that service, even though it's more expensive. But if our business requirements are for a database to be always available, usually that's worth the money to do it. And so our third peak would be like that, would be brick house, replicated database, highly available, the best you can get. But I don't know about you, but when I was a child, when I was reading this story, I always wondered, like, this wolf is kind of stupid, right? Because it tries to get to the pigs through the chimney instead of just kind of laying around, laying siege and waiting for the pigs to come out, because they will come out, they need food, they need water. Like, it's just not the right solution. And now, as I'm older, I'm thinking, if you were wondering about that as a kid, you probably was destined to become an engineer. It's kind of, you question the system like that. And on the other hand, if you're thinking, well, the pigs, why they're not in the safety of a pig farm? I would bet money you're a manager or like VP these days, if that was your like line of thinking at the time. But this fable of three little pigs was written before the first distributed system papers were published. And if I were writing this story today, I would title it Four Little Pigs, not Three. And the fourth pig would be the most like forward-thinking, the most thoughtful of them all. Because that pig would not build just one brick house. It would build two of them, and ideally far apart, and build a tunnel to connect them. And then they need to be far enough so there is like a mountain range, there is a forest and the river, so that if that hungry wolf comes and starts huffing and puffing on the side, our pig would just move through the tunnel, and the wolf would have no idea how to find the pig anymore. I would call this pig the Lamport pig, even though like Leslie Lamport would probably go for the three houses at the minimum, but I'm sure he would approve the general design. I know Louis tried to invite Leslie Lamport for a couple of times, so far unsuccessfully. But I think in honor of Leslie Lamport, let's call it the Lamport pig, in a good way. So that what Lamport pig chose to do is to go for geo-redundancy. Have these two houses, connect them, and be able to move between them, kind of fail over to the other brick house, which is better than having one house. And so we went with redundancy. What are the implications of that? What do we need to think about now, what we didn't have to before? And the first thing is data consistency. And it's kind of fancy word for having the same data like in both places in this case. Because if we have these transactions on one side, we want the same view of the world on the other side. And for that, we need some kind of replication protocol, because of two physical systems, two complete stacks, we need send data, we need them to be consistent with each other. And so there's really like two options. There is synchronous replication, which is simpler, easier to understand, because we kind of update all replicas in this example too at the same time. There is no same time in physics. So in fact, we just don't acknowledge the write until we got X from both replicas. Or if we use like the quorum algorithm, we have multiple replicas, like the majority. So we delay responding that operation is done until we successfully written these changes in both systems. This is all great. It's very easy to program against because things are always consistent. We always like view the same view. The irony is that by doing that, we lower our availability. So we're kind of building a reliable system, but now mathematically our availability is less than with a single system, because if outage of any of this replica essentially makes writes impossible, and then probability of our availability went down mathematically. And so it's ironic that we kind of got a counterproductive result. Of course, we can solve it with like 3 replicas with quorum, but then there are other downsides that are not always thought about upfront. Like if we have only 3 replicas and say 1 write of the 3 fails, it's a very dangerous situation to be in, because any other failure leads to losing of data, and sometimes very sneaky. And if you run some like distributed database like Cassandra in production, you probably encounter that if there's a failed writes and then there is no read repair, you need to essentially scan the whole thing, the whole table, and it's very expensive, it impacts performance. So like nothing is really free, but running like 5 replicas would be 5 times the cost, right? So it's also questionable. So there are always these trade-offs. The other thing, the downside of this approach is latency. Like if we put our replicas geographically, like usually in the US it's East and West Coast, they're like maybe 60 milliseconds apart, like round trip, maybe 100. So for any operation, we add this additional latency. Instead of just writing to local replica, we write to both. And some consistent protocols, most of them require multiple round trips. So applications that are latency sensitive, like some financial transactions or things that face the customer that pushes the button, they're sensitive to latencies going to hundreds of milliseconds from like dozens or from single-digit milliseconds. So like nothing is free in our profession. That's why we need to consider these downsides. And they're fundamental. Like we can do this replication, synchronous replication at application level, the protocol I described, or we can do it at the bottom, at the database. And in terms of cap theorem, in this case with synchronous replication, went for so-called CP system, where we sacrifice availability for consistency. That's what I also usually call CP and AP system, like 2 types. This is an example of a CP system. The other option is asynchronous replication, where instead of waiting for acknowledgement from the other replica, we immediately respond when we successfully written to the active replica. And then we have some kind of log shipping protocol that sends these updates to the other replica, and they asynchronously eventually get applied. So they arrive sometime later, and that's why it's called eventual consistency. So that's what it's called in the cap theorem AP system. We sacrifice consistency because if our system went down, if our active replica disappeared before a replication happened, our passive replica does have all the data. And if active disappeared in theory forever, the data will be lost. Or if it disappeared for a long time, the data is unavailable, it may create some kind of consistency violations at the application layer. And again, those trade-offs are fundamental. We maintain high availability, same availability as a single system. We have very low latency because we only acknowledge when I have 1 replica, but we went for eventual consistency in this case. Again, the same thing, whether with the application layer or a storage layer. So kind of intuitively, we want to go for asynchronous because we get good performance, but also we get this eventual consistency. How do we deal with that? And our industry has standard tricks, right? So one of them is event sourcing. So instead of writing state of an entity, we create a log of changes. It's a read-only, append-only log where we append updates, and then we ship those updates to the replica asynchronously, so that we may not have all of them yet. They may be like in transit, but the software is written with event sourcing style. It expects that those things may arrive later, these events, and they can be reapplied, and then any kind of aggregates can be recomputed, any notifications can be sent. So like when you choose event sourcing as your paradigm working with storage, your application generally can handle that. The other trick that is critical for this kind of eventual consistency is idempotency. So each operation we append, it has a unique ID, so that whenever it gets applied, whenever it tries, whenever it's timeout, we don't execute the same operation twice. That helps us not commit like double deduction from like a bank account. And really, the idempotency is so pervasive today in our distributed systems that I would say the internet would not work as we know it without idempotency. It's such a fundamental technique that we all use. So it's all good, like sort of theoretical concepts. They're clean, that's easy to understand. But usually, like, we want concrete example, kind of a real thing that illustrates those concepts. And I'm going to use temporal for that, temporal durable execution. I would say if you've not heard yet about durable execution temporal, you're like missing out. This is a very kind of hot technology these days. I work for this company, and that's not the reason why I say that. So Temporal is the company that pioneered this notion of durable execution and sort of productize it and build on that. I'm not going to dive into like details of how Temporal works, what it gives. I gave other talks, and you can find a bunch of materials. But kind of a 30-second summary is that it allows us to write happy path code where we write business logic in terms of what needs to happen. And whenever something doesn't work, when we call API and it returns 500 or 429 to, like, say, throttling us, or some other retriable error, we don't need to write code for retrying, for like exponential backoff. All that is done by the system. So it allows us to completely kill our application and then restart. And all our business processes, we may have thousands, millions, billions of them. This individual business process that, for historical reasons, called workflows, they continue executing from the line where they stop when the application crashed, for example. So you kind of make this application fault oblivious. So you write as if failures never happen, and then they sort of hidden away from application logic by the system. And that's why it's getting so popular. I could go into the history and sort of how it happened, all these companies that use it. I'm not going to do it. What's kind of relevant for this talk is that the programming model of Temporal essentially was built with event sourcing as a fundamental characteristic. But instead of event sourcing data, changes data, it records in this append-only log history of execution of each business process, of each of these workflows. So you may have millions of them running, and each one of them has their own sequence of steps. So whenever application code needs to do something, like call the API, in intent to call the API gets recorded in history, say, try to call this API with these arguments. And then if the call succeeds, it records the response was whatever, XYZ. And that gets restored in history. And that allows for this kind of replaying and restarting application. We can shut down our logic, our whole process of application, and start it, and then we'll go through this kind of replay process, say, okay, this step's already completed these results, and reconstructs application state without re-executing those calls. So it gives this illusion that execution starts from the line, from the next line in the code. And so because it's kind of done this way, there is a strong requirement to idempotency. Like if you're making a call to another API, it has to be idempotent. Like any kind of side effects, they have to be idempotent. And on top of that, the business logic, it has to be consistent when it executes. It cannot change logic on the way. You cannot deploy a change that changes like forks the logic. You have to like work around it. So there are very strict requirements for determinism of execution and idempotency. So we kind of get all these techniques that I mentioned before, but applied to code. And I was presenting this a few months ago. The old-time friend of mine, he was like, oh, now I get it. Because he was a big fan of event sourcing. He said, I always thought event sourcing applies to data, and this durable execution applies event sourcing to execution. So that's what I can name durable execution kind of makes sense, because we make durable what is the step, what is the state of execution of the application, not just data. And so naturally, this kind of organization of this program role makes it very compatible with asynchronous replication, because we can ship histories to the other replica. And it's okay if not all of it is available right away, because generally, like, it keeps coming, it'll be there within like tens of milliseconds, maybe 100 milliseconds. And if you need to fail lower, and we eventually consistent, even that not a huge deal because of this determinism of execution. In most cases, even if we were to lose some of the events, in most cases, those events will be recreated by the business logic, which is deterministic. So it kind of generates the same events with the same inputs they already got into it. There are some exceptions to that, like, for example, like human input or some kind of external signals that if you lost them, you will not be able to recreate them. But by and large, it just works on itself. So even though it's eventually consistent, it's also kind of like strongly eventually, a strongly consistent flavor of eventual consistency, if that makes any sense what I'm saying. And so in this case, again, we implement the AP system where we sacrifice consistency a little bit for eventual but kind of strong flavor, but we have high availability because we can fail over to this replica anytime and application continues to execute. And these millions and maybe billions of business logic instances, like even if 2 of them got in trouble because there are some signals that are lost, the rest of them will keep going and you just need to fix, in the worst case, you need to fix a few of them. So how it works. A few months ago, we announced a general availability of replicated namespace. And what is a namespace? I think of it as kind of like remotely analogous to GitHub repo or some kind of execution database. So how it works, code runs in this worker processes at the bottom. And workers talk to this namespace. They have that kind of high traffic to record every action. So execution doesn't happen in namespace. It only happens in the worker process. But all histories are written by this namespace. So think, it's not the exact analogy, but if we were to add commits to GitHub repo constantly for every line, it's kind of similar conceptually. So it talks to this namespace through the SDK that does automatically as part of the runtime. And so normally when you create a normal namespace, you create it in a single cloud region. But then you can add a second region. And in this case, it starts replicating immediately. You add a region, it starts replicating, and when it replicates everything that's already in the active replica, it's ready for a failover. And if we failover, now what was passive replica becomes active and starts replicating back to what used to be active and now passive. So we kind of can go back and forth and be reliable. Like if there's any issue, or if there's any concern. In fact, we even recommend people to perform failovers. They can schedule like daily or weekly just to test that the application works. So this fundamental mechanism, it makes a bunch of other things available. These replicas of a namespace, they don't necessarily have to be in different regions. They can be in a single region in different clusters. And we actually heavily use it for years before publicly making it externally available. We use it for moving, we've been using and continue to use it for moving workloads internally. So like customer has namespace, they didn't know that we create a new cluster and we start replicating their namespace, create a replica of their namespace in a different cluster, that we replicate everything, and then we fail them over to this cluster. They have no idea that happens, but we moved data, maybe we shut down the old cluster, or we can do anything. We can bin pack, kind of rebalance load. So we've been using it for that purpose, kind of internally, before we gave benefit of that for the customer. But then this kind of application level replication, it has no dependency on anything below. It's not like reasoning a replicated database. So we can set this to namespaces in different clouds. We can replicate from AWS to GCP or to Azure. And in fact, some of our customers are doing that migration. Like I think some of them are moving from AWS to GCP right now. Imagine doing it with other technologies. Because again, if you have experience of running something like Cassandra in production, you understand how difficult it is to deal with that at the data layer. And database will never be as smart as application layer because it just has rows and tables. But here, you know, okay, this is context of this business process, this history, and this and that. And you can optimize, you can batch, you can do a lot more at the application layer. This is a most favorite question of kids when you drive them somewhere in the US. Keep asking that. Of course not, because we just solve, in this case, a replication of namespace problem. We still need to look closer, right? Like if we run in workers in the same region as this namespace, even if we fail over the namespace, because of the issue with the region, what if our workers suffer from the same region? It's not as reliable as having everything. And so that leads to kind of running 2 copies of workers at the same time. So if we fail over, we have workers that are not impacted by any outage in the original region. But real systems are even more complicated because they have a bunch of different services interacting with each other, which usually people with different namespaces, but they may also have some kind of stateful dependencies like the databases. So originally, this whole technology was built as part of Cadence, which is precursor to Temporal, was built at Uber. And Uber at the time, and I think still around, they had 2 physical data centers that they operated. And the requirement for like whatever we call it, tier 0, tier 1 services, they had to run with 2 replicas into data centers to be able to failover. And interestingly enough, and it was counterintuitive to me, most of these teams were against automatic failover. They didn't want their namespace to be failover when some issue is detected. They wanted to have control so that they can failover multiple namespaces. They can do something with their database before failing over namespaces. So again, like real-life examples are more complicated than simplified kind of theoretical concepts, but concepts still apply. You just need to consider more factors when building a real system. Now, going back to the trade-offs of business, some applications, some services, they may not justify the cost of running this full replication because we need to run 2 copies of the same stack at least. And that may not be worth it for things that are not as essential. Like, for example, some scenarios when they process a bunch of requests, a bunch of like social media posts, and there is a queue to process. We don't necessarily care, like we're going to have these 2 namespaces, and if we fail over, we may leave those that were being processed in the original active behind. We can just start using a new namespace. It's a pattern is called standby namespace, where if there's any issue with one, I just change my application and start using another one. If something completes there, it's fine. If something is incomplete, it will be retried by other means, by like queuing. And in this case, I'm not using double resources. I just use one at a time, essentially. The other version of this approach is instead of keeping this second namespace standby idle, I can divide my traffic 50-50 and use them as active-active, both of them. And in fact, I don't have to have 2, I can use 5. And I can spread 20% of traffic to each of them. So like if one goes down, I only need to redistribute 20%. So each one of them gets quarter more load, which is very manageable because they always have headroom. Kind of the downsides you pay for that is that if you need to look up like what happened with particular business process, you have ID, now you need to find in which namespace, like what was the mapping the time it happened. Was it 5? Was it 4? Like some kind of consistent hashing or some recording scheme. So there is more complexity. You cannot query all of them at the same time. So you pay some convenience for developers by going with this kind of simple dynamic sharding scheme. And of course, as I mentioned, like the workers, you want to also distribute them. And kind of the end version of this pattern is you shard namespace and you shard your workers so that they all can talk to each other. And you lose one replica, that's totally fine. That's just handled. Everything works everywhere. So what I want you to take away from this talk, the first claim I would make is reliability, even though people don't talk about it this way, it's somewhat similar in some aspects to scalability. Like scalability will scale up, and at some point will scale out. So I would say the same happens with reliability. We can make local system more and more reliable by adding more complicated hardware, software, local replication, but then there's kind of phase change. We need to go distributed. We need to go geo-distributed. And that changes the rules of the game. That changes some of the considerations and fundamental trade-offs. And again, going back to the very beginning, the key question is, what are the business requirements? What are the business risks? What are the costs? What are the probabilities? Because it's stupid to build expensive, very reliable system for something that's not worth it. But in other cases, it's not even driven by business risk, it's driven by regulation. I think in EU, they're trying to drive these requirements to financials that they should not be down if like one cloud provider is down. They need to have redundancy across cloud providers, which this technology solves right away. You can just plug and play, essentially. So there's kind of 2 dimensions of getting high availability, building reliable applications. That's one thing. I hope I made a compelling case that application-level replication is always more flexible, more powerful, because you have more control than lower-level database replication. And it's not just that data is like low level, it's oblivious to kind of high-level semantics and opportunities for optimization. It's also, if you look at distributed databases, geo-distributed databases that offered by cloud providers, they're all single cloud provider. So like, if we were to go for like RDS Aurora, you cannot move to GCP or Azure. If you go with Cosmos DB, you're stuck with Azure, same with Spanner and GCP. But if we do it application layer, we have this freedom. We can use, and we can even like, connect to on-prem systems and replicate between cloud and non-cloud systems. The choice between synchronous and asynchronous application, it's purely a trade-off, the cap theorem. Do we prefer consistency and simplicity of application, or do we prefer high availability, even if it sometimes costs us some inconsistencies, some eventual consistencies? And there are ways to improve that. Durable execution, like I said, you can look it up. It's a very hot topic. There's big companies, they really jump in this bandwagon, and you can read a lot about it. And I'm sure you'll be, if you haven't heard of it, you'll be thanking me for pointing to it. And maybe you'll come to JOTB25 just to thank me for pointing to that very hot trend right now. And again, I'm not saying it because I work for the company. It's like really, you talk to these big guys like Netflix is surprised what they say, like, oh, this changed how we build software, essentially. You hear that from people that know how to build software. And lastly, when we build system, we cannot just take a simple solution and apply it everywhere, because we need to have a bigger picture and look at all the pieces, all the moving pieces on the application, in the whole system, and understand trade-offs. Again, never forgetting about the business aspects, because engineers tend to go for something that's cool, something that they want to build, something that is great, but they always need to challenge them and ask, what's the business value of doing that? So that's why we need to look at the whole thing, understand the value of it brings, understand the risks and the cost from building operational costs, which people always neglect or underestimate operational costs, but also opportunity costs. So we spent 2 years building this, what are we not building in these 2 years? So always look at the full system. And thank you. I hope we'll write this 4 Little Pigs fable someday.